from Nottingham is going to be our speaker.
You've got too much hair.
Don't worry about the ears, just put it over.
Is it working now?
Yeah.
Yep. Cool. Right. I'm Jenny Hackett from the University of Nottingham. I'm talking about worker wrapper makes it faster. The paper is a joint work with my supervisor Graham Hudson. So you might notice there's a picture of a cauldron. So that's kind of a terrible pun. We all want some kind of magic spell that we can cast on our programs to make it go faster. And so we thought we chose the title because it's sort of rhythmic and rhymes a little, a bit like a magic spell. So if you cast it on something slow like a snail. So what's this actually about? Well, there's a lot of research into correctness optimizations. People studying how can you prove that some program transformation doesn't change what the program actually does. We can talk about the meaning is preserved in some sense. There's significantly less work on improvement, which is how can we be sure that the program we get out is actually better. I mean, it's actually quite a difficult problem, especially for lazy languages like Haskell, so it's not that surprising. So we've decided to address this problem in the case of the worker wrapper transformation, which is a general purpose optimization. We've done a number of papers on it in the past. So here's an example of the worker wrapper transformation. You start with a slow function. In this case, we've chosen the naive reverse function, where you just you reverse a list by crap. Sorry about that. You reverse a list by taking the head of it off and adding it onto the end. Keep going until you've got nothing left in the original list and you've got the reverse list. But that's quite slow because you're using appends a lot. So you want to maybe replace it with this faster version, which I will call it fast reverse, where you have an accumulating parameter. You start with the list, you take elements off one list and stick them on the front of the other one until you've got nothing here and the whole list here, but in reverse order. So we want to be sure that this is correct, meaning we want to be able to use the new reverse function exactly what we had used the old reverse function, and it wouldn't change what the program does. And we want to make sure that it's somehow more efficient, or at the very least, we don't want it to be any less efficient. I mean, so in reality, the top function is quadratic, but the lower one is linear. But you have to prove that sort of ad hoc in this case, and it doesn't transfer over. So here's the worker wrapper transformation in a picture. You start with an original program, and you split it into a worker and a wrapper. So the original program was type A, the worker has type B, and the wrapper converts from the type B to the type A. And hopefully, if we mix the yellow and the blue on the right-hand side, we get the green on the left. So let's try and make that a bit more formal. In this case, we're going to say, let's say we're working with a general recursive function written as a fixed point. So we've got fix of f has type A, so f is of type A to A, and fix of g has type B, so g is of type B to B. And we have an abs which abstracts from type B to type A. And we also have a function rep, which represents things of type A in the type B. So abs and rep have some relationship. So this is the worker wrapper theorem for correctness. If you have these functions f, g, abs, and rep, and if abs after rep is h, meaning if I first represent something in the type B and then abstract it back into type A, I should get back what I started with. And we also want g after rep is rep after f, meaning it's kind of like a fusion condition. If you push a g through a rep, it should turn into an f. If you have both of those things, you can conclude fix f, the original program, is abs, the wrapper, applied to fix g, the worker. And we hope that fix g is better in some sense than fix f. So for fast reverse, we take this abs, rep, f, and g. I'm not going to go through the details, but it's fairly trivial to prove the first assumption. And the second one is quite simple as well. You don't have to do anything like induction. The induction is sort of captured in this theorem. So you don't have to worry about doing it sort of individually for each case you're concerned with. Right, so that's all very well and good for correctness, but where does it leave improvement? So we want some way to compare the cost of two programs. It's like I said, this is difficult, especially for lazy languages. The naive approach would be to count steps you take to evaluate to some normal form. So in maybe the weak-head normal form or a beta normal form or something like that. But this doesn't really work. I mean, if you consider the two terms there, if we talk, they're both already in a weak-head normal form. The one on the right is actually in a spine normal form, meaning that the spine of the list is normalized. We don't know what any of the elements are. But in general, you can't replace one with the other one and expect the program to do the same thing or to do any better or anything like that. So actually what we need is a precongruence. So a precongruence is a particular kind of relation. It needs to be that firstly it's a pre-order, meaning it's reflexive and transitive, and it's also a congruence, meaning it's preserved by substitution. So the reflexive and transitive captures sort of fairly intuitive ideas of what an optimization should be. We should say that there should be some obvious relationship between a program's efficiency and its own efficiency. And if we improve a program sort of twice, we would like it if the whole thing was just the same thing as improving it overall. And congruence captures the property that we've got on the right there, the little picture. If we want to improve a whole program, we should just be able to improve a bit of it. And that way we can improve like a bit over here or a bit over there, and eventually, you know, we have a whole thing. So we don't have to worry about effects where different parts interact. So if something has both those properties, we call it a precongruence. So Moran and Sands in '99 had a solution to just, you count steps taken in all contexts. So you quantify a broad context and say, how many steps? And so you have to compare, so if you want to compare two terms, you need to compare them in any possible conceivable situation. In this case, they counted only lookup steps in the Sestov Mark I abstract machine, because it turns out that the total number of steps is linear in the number of lookup steps. So we have this definition, we say M is improved by N if for any context C of M takes at least as many steps as C of N. So this sort of improved is a sort of at least property, which basically means N is at least as good as M in all situations. And we also have this notion of improving with a constant factor, which is basically that, but we also have a linear function on the right-hand side, and that allows us to worry about things like, well, suppose N is basically better than M, but maybe sometimes there are a few corner cases, or maybe it needs a bit of startup cost or something, but N will never take more than, like, let's say twice what M took. So if our machine is fast enough, maybe we don't care about that, so it'll slow down. We hope it doesn't happen all the time, of course. There's also, so improvement theory has a number of interesting and useful rules, but this is kind of what I think is like one of the more useful ones. It's called improvement induction. So basically, it's a way of reasoning about, you're given two terms, as long as you can find a context C that makes that work, then you have a relationship between those two terms. This also includes this tick, that sort of represents a single unit of time cost. You can actually encode this in the language of improvement theory just by writing it as a let binding, but it's sort of easier if you just have a separate operation for it. And then we can, a lot of what we end up doing is pushing around ticks. So if we if we can somehow turn M into a tick of C of M, and then turn a tick of C of N into N, then we know that M must be improved by N. And in the paper we use this to prove a fusion rule and a rolling rule for recursive binding, and these are sort of the core of the work graph technique. And this is kind of like guided co-induction. So, this is probably going to be meaningless to anyone who doesn't know what guided co-induction is. I'm very sorry. So it's like guided co-induction because it sort of involves taking a term, unfolding it to the point where it sort of has itself in there, making a substitution and folding it back up, and then that substitution is valid. Is valid as long as it's guarded by. In this case, it's guarded by a tick. In the case of guarded co-induction, you want it to be guarded by a constructor. But the idea is, this proof sort of looks circular, but the fact that it's guarded by a tick means it's not really circular. Just like guarded co-induction. It's sort of, some people describe it as a bit like induction without a base case. I think it's slightly misleading, but yeah. So, that's the worker wrapper theorem we had before. If we just sort of translate this into language improvement theory, we end up with this. So, we started with functions f, g, abs, and rep. Now we have context abs, rep, f, and g. The type information on it has disappeared because improvement theory is an untyped theory. I'll get back to that later. And if these assumptions have then turned into improvements, but actually there's two different things at play. Firstly, we have that abs rep x needs to be equivalent to x, but only sort of weakly equivalent, meaning you can have a constant factor in there. And the reason it's not a complete sort of strong equivalence is that if it was a strong equivalence, then abs and rep basically wouldn't be able to do anything because they wouldn't have any time to do something. And then the g after rep equals rep after f is replaced by this. Rep of tick of f of x can be improved by g of tick of rep of x. So you notice the tick has appeared there, that's something that we needed to make the proofs work, basically. And the fact that f is on the slower side of this and g is on the faster side, that's sort of where intuitively where the fact that the implementation with g will be better than the implementation with f. And then if we have all that, we can conclude the bottom bit, which is a weak improvement, an improvement within a constant factor. You start from the original definition of the original recursive definition to a new recursive definition, which is wrapped by the context abs. And then if we take all of this for the fast reverse, again we just translate stuff. We just translate the definitions we had before into the language of improvement theory. Then we can do more or less exactly the same proofs. There's a bit of extra bookkeeping. We need to push around ticks, and there are some rules that are a bit finicky, but yeah, basically the proofs are more or less the same. And in fact, you could skip straight to this proof, but personally I think it's easier if you start with the correctness proof, because then you can use this as a guide for the improvement proof with the extra details. I'm running very fast, I'm sorry. So it turns out we can make rigorous arguments about the efficiency of lazy programs. And we can use this kind of argument to make a performance guarantee for a general purpose optimization. And as far as we're aware, no one's done this before in a lazy context. And the conditions of that it's an improvement are fairly naturally related to the ones that for being a correctness. You just sort of translate from the language of one theory to the language of another theory. And because of that, the proofs both of the theorems involved and of the examples are essentially the same. We cover 3 different examples in the paper, and of which the fast reverse is one of them. And they're all from previous worker wrapper papers, and we get the proof more or less by adapting the original proof into the sort of language and adding bits and bobs, tweaking it until it goes through, more or less. In the future, there's a number of things I will look at. firstly, the obvious thing is, well, we've got this for fixed points, but we haven't really talked about structure recursions. That's an obvious thing to look at. As I said before, improvement theory is untyped. There would be some advantages for it being a typed theory. I mean, the obvious one is, in a typed theory, rather than having to concern ourselves with every single possible context you could possibly conceive of, we only need to worry about contexts where the types actually make sense, which makes a lot of the proofs significantly simpler if you have to actually prove things sort of using the raw definitions. I like to look at space as well as other resources. There is an improvement theory for space, but it's different enough from the one for time that we can't use this. Basically, there's no rule like the improvement induction rule, because that only works for time-like resources. And also be good to look at other resources. Quantified improvement, what I mean by that is, we're talking about, can you replace X by Y, and will that make things worse, or will it possibly make things better? Whereas quantified is sort of asking the question, how much will this make things better? But at the moment, we don't know. If we have two different optimizations to choose between, we don't know to go for the left one or for the right one. So it'd be good to have some idea, of how to choose between those two things and how to judge, and making that as rigorous as possible, of course, would be a goal. And finally, automation. So the worker rapid transformation has been automated in the Hermit system, which is a system for applying program transformations. It would be nice to implement improvement theory in a system like that, so you can, because like I say, there's a lot of fiddly details to the proofs. I mean, the broad strokes are very simple, but the devil is in this case in the details. So it would be good to have a system to help you with those proofs, and then sort of for in the future to automate this whole thing and putting it into some kind of system would be a goal, I think. So that's all I've got to say.
Hi, I'm Jeremy Gibbons from the University of Oxford. Thanks for a very nice, clear talk. You've shown us some kind of soundness results that this improvement technique, will, if you can use it, will guarantee that your transformations don't make things worse, according to this definition of worse. But do you have any completeness results? Does this always apply to worker wrapper style transformations?
So basically, you're asking sort of. Well, if you're so for the fixed points, basically what you're saying is if I might translate this question kind of, if you have, can you always translate the proofs from here to here is kind of the question you're asking. And the answer is, it's not clear. So I think my personal belief is it's limited to certain cases of abs and rep. So it's this condition on abs and rep here is kind of the thing. It limits you to having abs and rep functions that sort of do sort of constant or some kind of limited amount of work. If abs in particular was doing a really complicated job, that means that's basically like saying maybe the startup cost of the transformation is so big that it's likely to overwhelm the benefits. Certainly, I think, though I haven't formalised, if you have these, you can go back. But it's not. But I certainly don't think it's. I don't think it is the case that if you can go forward for any transformation. Though I think it might be nice to somehow try and characterise the class of transformations where you can do that.
Thank you.
I'm Paul Liu from Intel Labs. My question is sort of related to your previous one. Do you have any counterexamples whereby applying Walker-Weber transformation make the performance worse?
I think so, though of course we wouldn't want to put those in the paper. I think while I was working on some earlier work, I came up with a few things about well, the idea was to try and optimize tree traversal by some particular forms of tree traversal by transforming the tree you were working on and into a different form. The idea was that new form would be easier to traverse in the winter, but I wanted to. But the problem was that doing the transformation of the traversal sort of overwhelmed any kind of gain you would have gotten. So I guess that's kind of vague because I don't remember the details, but I hope that answers.
Thank you.
What the improvements, all the theorems are stated in terms of algorithmic complexity. And yes, of course, it's nice to see that Walker-Rapid transformation and some given assumptions improve the algorithmic complexity. But you always emphasize lazy languages. But for lazy languages, the performance of epistemization comes from space, and time is indirectly from space. Here's an example. For example, we know that when we do fold some elements of lists, then we can, well, in old version of GHC, we run out of memory because we construct this big thumb, which we force later. And it also, well, of course, it's a bad space complexity, but it's also there is a time complexity because there is a time of constructing the thumb, which is forced later. Right? And that's what actually where the problems in reasoning about time complexity in lazy settings come up, because there is also a cost of building a closure. So I'm interested, well, how this cost, which is very indirect and doesn't appear in the program, of cost of building closures, how is reflected in your framework?
So like I said before, this is based on early work on improvement theory, of which I will happily admit I don't understand all the details of. So I suggest you read the earlier papers. Maybe that will help answer the question.
Joachim Breiter from Karlsruhe. So from what I can see, your theory is correct when the transformation happens to be a non-improvement in all contexts. But in practice, when I write an optimization, I often first find out in what context is this being called, and I might find out that this context always evaluates the second element of a pair, but not the first in the result. And I want to do a transformation that improves in this particular context. So is there still a theory there, or is it just that I can't apply these methods if I'm only looking for a transformation that happens to be in only some context, and I don't care about other contexts?
So, it sounds like for truly global things where it depends on everything that's going on, and this isn't going to help. It sounds like you're talking about as a sort of limited, the nearby bits of the context, what you're immediately doing with the result is going to help, is going to be the important thing. And so I don't think that this is going to be directly applicable, because this sort of deals with a situation where we're looking at a recursive binding with nothing around it. But it's possible that, later attempts to generalize this sort of might help with that.
Okay, thank you.
Final question.
Hello, this is Neil Krishnaswamy from the University of Birmingham. So I have sort of the opposite of Oleg's question. Sort of looking at your proofs, it looks like you're sort of working in a credit-debit style, which sort of fits very well with laziness. So if you wanted to apply these kinds of improvement proofs to a call-by-value language, would things change very dramatically?
So you couldn't use the exact same proofs, obviously, but you can do the same thing with call-by-value and generate a theory of sort of its improvements, and I think there's been some work on that. My main interest is on call-by-need, precisely because it's harder to reason about. Call-by-value. There's no point in trying to do something if it's really easy.
Thanks very much.
We now have a break, but I have a request from the recording people.